Have you ever experienced that frustrating feeling of waiting for an email attachment to be downloaded? The files that we download, like pictures, videos, and sounds,
In a minute, I'ma need a sentimental man or woman to pump me up. Feeling fussy, walking in my Balenciennes, trying to bring out the fabulous.
on a daily basis took up storage. After all, we ideally want to have a lot of storage space along with fast transmission of data to the other end, right? The answer to this dilemma is data compression. Data compression is done in different data formats in order to reduce its size for a more efficient saved space. However, as we may think that reducing file sizes saves our storage's life, it is also a double-edged sword as it may also be inefficient. Let's imagine going to the grocery store because your mom told you so. She gave you a list that contains multiple peppers in it, totaling 10. Imagine if your mom does this to the other needed items as well. Wouldn't it take too much space of the paper? If we apply data compression here, we can replace the original representation of the repeatedly occurring data into a compressed one by simply putting its total quantity behind each item, making it a lot efficient and saving much space than before. Now that you have a preliminary knowledge of what data compression is, let us now discuss its two major forms, which are lossy and lossless compression. In lossy compression, as you continue to compress the data, its quality degrades over time. Take this picture as an example. If we went and compressed this image by 25%, we won't see any major differences visually compared to its original quality. If we go further and compress it by 50%, we could see the image starting to look blurry. So yes, it does indeed save space by compressing the data, but at the same time worsens its quality. Some of the lossy data formats include JPEG and MP3s. Lossless compression, on the other hand, is a type of compression that does not affect the quality of the data no matter how much you compress it. The company Apple introduced to its users a new type of audio format that delivers a high-quality sound to the users. The Apple Lossless Audio Codec, or ALAC, allows users to listen to songs losslessly, which gives the users a good quality of listening time with resolutions ranging from 16 to 24-bit. Some of the other data formats of lossless compression include GIFs and PNGs, one of the two major data forms of data compression. The Lempel-Ziv algorithm, created by Abraham Lempel, Jacob Ziv, and Terry Welch, and improved by Welch in 1984, the Lempel-Ziv algorithm works by creating a dictionary by which is encoded without knowing how frequent it appeared on its original message. The encoder of this technique will start to assign the content of the original message uniquely from each other. However, if a similar code had been encountered before, it is not deemed to be unique anymore. And so, that code will be attached to the next code or number for identification, whether that newly formed code appeared already or not. The main essence of the Lempel-Ziv algorithm is to send a compressed message along with a dictionary of codes to the receiver. This eliminates the need to send a unique dictionary after sending the compressed message to the receiver, which will delay time for decoding. Treehouse Wars. This game is composed of 4 players played by pair. You and your friend against your 2 other friends in 4 parallel trees away from each other. Now, imagine how can you strategize with your teammate positioned on the other treehouse from you without the use of any gadgets. Let's say you use Morse code. Given that your friend has no knowledge of the secret code, your friend needs to have a code book for Morse code so that your friend can understand the message you are trying to send across. But as you proceeded in sending the codebook of Morse after you send your message on a paper to your friend, the enemy already has made its move and attacked your base, making your team lose due to miscommunication. But what if we do it this way? What if you send the codebook with your compressed message in it, and as you send only the compressed message to your friend on the other side, they can use that compressed message alone to create their own codebook, same as yours, to decode your message. Seems more efficient and fast, doesn't it? Now you might be wondering how these messages are encoded and decoded. Let us proceed with an example. If you are given a binary string of 0160110. First, we construct a 3-column table with dictionary location, content, and code word placed in each cell. To start, we identify the first bit in the given string, which is 0. This is the first time that we encounter the bit 0, so we put it in our first content column. We do the same step for bit 1. Followed by 0, 0, this is also unique, so we put it accordingly. Repeat the steps until you reach the end bit of the given string. Now that our content table of unique bits is complete, let us proceed in labeling our dictionary location. In labeling our dictionary location, we identify how many unique bits we have come across with. In this case, we have 6, so just put the increasing order from 1 to 6 in each cell up to the last unique bit. Transform these singular numerical values into bits, and these are the values which correspond to each numericals. For the last column, in identifying the code word, we must consider two things: the least significant bit and the prefix bit. The least significant bit is the bit farthest to the right of a given string, while the prefix bit is any bit that comes before the least significant bit. We put 0 to the rightmost part of the code word column, and since it has no prefix, we fill it in with 3 zeros. Same goes as the next content of 1. Now that we encounter the prefix, we will now look at our content column and look for the content by which our prefix is identical. After we identified which content is identical to our prefix, we put its dictionary location as the prefix of the code word. So if our prefix here is 0, we look at the 0 content cell in its corresponding location, which is 001. We put this beside our least significant bit, and we do this process until we finish it all up. In the decoding process, we align all the gathered code words in ascending order starting from 0000 up to 0100. Construct the same table as before. This time, start at the code word column where we put the constructed code words from the encoding stage to this column in ascending order. Put the least significant bit again to the rightmost part of the content column, and if it has no prefix, then just put the least significant bit by itself. If a prefix is found this time, after we identify the prefix from the dictionary location, we check its corresponding content bit value and write that after our least significant bit in the content column. Repeat the process until you complete the table. After completing the content column, start to align the values from top to bottom next to each other. In this example, after doing so, we get 0160110, which is the same binary string as the original binary string. Therefore, the code bit has been successfully decoded by the receiver without losing any information. Published by David A. Huffman in 1952, Huffman coding is evident in different media we use daily, such as MP3 and JPEG. Essentially, this compression technique can be used in some data which has frequently existing symbols, and translate that to a lesser number of bits. The most frequent symbol is designed to have the smallest code sequence, while the least frequent symbol is assigned to have the largest code sequence. However, the decoding stage of Huffman coding may present different possibilities for each translated code, which creates ambiguity. That is why prefix codes are present to avoid this from happening. Prefix codes are created using a binary tree by assigning bit strings to symbols with reference to their frequency. Say we have the word good afternoon. Create a frequency of occurrence table with the symbols along with their number of occurrences. Create a priority queue table with the least frequent symbols on top and the most frequent symbols at the bottom. Start connecting the least frequent symbols together by joining the root nodes together to form a new node. Symbols AD, EF, GR, and T underscore. Observe these symbols all have their number of occurrences of 1. Update your priority queue by moving the unpaired symbols upwards and the newly formed nodes beneath it. Still consider the number of occurrences of these new nodes formed, and do not merely put them beneath the unpaired symbols without organizing their position based on their number of occurrences. Keep repeating the steps until all new nodes are paired with each other. In the case of pairing a number of occurrence with a different number of occurrence, 2 and 4, just pair them together and take note of their total occurrence. As you reach the last pair of newly formed nodes, connect them together and add their total frequency. The total frequency of the node T underscore O is 6, while the total frequency of the node NAD EFGR is 8. 8 plus 6 is to 14, and as you count the number of characters in our given good afternoon, you can see that they are both 14 characters long. Therefore, our tree binary is correct. Now, as the binary tree is complete, label its branches with 0 and 1, with 0 indicating it is a left branch and 1 indicating it is a right branch. After that, traverse down the branches with indication of 0 and 1, and as you go to the desired symbol, the Huffman code is now formed. Simply list all the codes starting from the first symbol all the way to the end symbol. As we count the number of bytes formed by Huffman code with 45 bytes, and comparing it with the ASCII code with 112 bytes, we can see that indeed we compressed the given example using Huffman code. From our regular emails to the comfort of listening to music, data compression is evident. It serves an important role in the database of any existing technology in the world. Now that technology continues to be improved and be innovated, billions and trillions of data are being transferred from one server to another. We all want to transfer files as fast as possible without having to experience delay. Without data compression, our internet community would be chaotic and you probably won't be able to watch this video right now.